I'm going to start today with an example from last time about convergence of limits of averages or actual limits of iterates of stochastic matrices. So here's an example, rather simple one, but it illustrates things. So we have two states, 0 and 1, and we have a full probability of transition from each to the other. All right, so that means this is our matrix here. Oops. This is our matrix here. And its iterates, well, so we just have two states and full probability. And notice it's irreducible. All right, so you can certainly get from any state to any other state. Or if you like, in terms of matrices, if you raise it to an odd power, you get it back again. Oops. Right, sorry, I thought I had that wrong. If you raise it to an odd power, you get the matrix back again, and if you raise it to the even power, you get the identity matrix. So no matter how large n is, you alternate between these two matrices, and so the limit doesn't exist. But if you average the sum in this Cesaro average or Birkhoff average kind of way, then it's clear you get more and more ones. You get a matrix with more and more entries here, 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 about the same size, off by 1, depending if you're even and odd, and then you divide by 2. So it converges to a half. So notice this is the proper form. And this is also the natural asymptotic measure of this system, because if you think of this as a Markov measure, the only state that has positive measure is the periodic orbit corresponding to these starting at 0 and going back and forth and starting at 1. So here, if we write them as bi-infinite sequence, we get this. So that orbit has full measure, and each element of the orbit has measure 1/2. All right, so 1/2 is, of course, an invariant measure because you have 2 points, each with mass 1/2, and it alternates from one to the other, so the measure is preserved. So that's kind of a simple example, but it shows irreducibility as opposed to being primitive. So the next topic is a different version of the ergodic theorem that's due to von Neumann, 1931 or something like that. And it's associated with L2 and the so-called Koopman operator, which often is given a name here. Isn't named, it's in the text is just the associated operator. But here's its definition. We've seen it before. We have a measure preserving transformation of a probability space, and the Koopman operator takes you from LP to LP by just taking the composition with F, or you precompose with F. Given your observable, you precompose with F. So the fact that this takes LP to LP is an argument using the change of variables formula, as is the fact that it has P norm 1. All right, so this is all P bigger than 1, less than infinity, say. So physically, if you like to think about it, it tracks the evolution of scalars, scalar fields, if you think more physically, or observables. It's the operator which takes the observable at one state to the observable at another state. So the example here, the simplest example, is let A represent a patch of dye in a fluid. So you have a fluid here, and I drew the picture before, and you have some patch of dye, and you let your indicator function represent the amount of dye. So you have your 1 if you're in the dye, and 0 if you're outside. You act by F, on the right here, and you get the indicator function, in fact, of f inverse of a, right? So we've seen this many times that the end, if you compose with f, you get an inverse here. So the operator acting on the die tells you where the die is after acting by f inverse. All right, so we've seen many times why f inverse is advantageous mathematically, but it's a little confusing physically because you'd like to go forward, but you can of course just go the other way if you have something that's by measure preserving. Like a fluid flow, one can consider the operator acting by the inverse, which in fact will be the inverse operator. All right, and then of course, as you raise it to the nth power, it tells you about how the scalar is evolving under n iterates. So the asymptotic behavior of the operator tells you the asymptotic behavior of observables, or if you like, you can think of this as cream in your coffee is the usual thing that's brought up. As you stir the coffee, the cream gets intermixed. So there's some action of the fluid flow gives rise to a measure-preserving transformation. And a fluid's called incompressible if the transformation of the fluid point to point is area-preserving if it's two-dimensional, or volume-preserving in 3 dimensions. So this was just a scanning mistake. So here's the LP ergodic theorem. So we're going to see eventually the L2 ergodic theorem, but let me just state the LP ergodic theorem. So 1 is less than p is less than infinity, and we have a measure-preserving transformation of a probability space, and we have an LP function. We have an LP function, and then, as with the pointwise ergodic theorem, you get a limit function, but it's a different kind of limit. There's some alpha star in LP, also an LP function, and it is an invariant function almost everywhere, and the alpha composed with after the I converges to, this is wrong here, sorry. So in LP, so it's important, so this is convergence with respect to integrals. Remember what LP convergence means. It doesn't mean that this converges to this pointwise. It means that the difference between these to the pth power converges when you take the integral. Or if we write it in terms of the Koopman operator, you get that the average values of the Koopman operator acting on alpha converge, again, in LP. All right, so here's a very rough sketch. I'm skipping all the hard part because they're going to prove in detail the L2 version. So if alpha happens to be bounded, all right, so LP doesn't mean it's bounded even in the interval case. But if it is bounded, and you write this term, this sum is bounded. All right, we've seen this before. We're taking 1 over n, alpha is bounded, so we take this average. It's bounded by whatever alpha is bounded by. And then we know also by the pointwise ergodic theorem that this converges to something pointwise almost everywhere. It follows fairly easy that this is also bounded almost everywhere. And then we know that alpha star is an LP because it's bounded almost everywhere. And we have that convergence in LP using the bounded convergence theorem. So I've mentioned this before, and I'm sure you saw it in your analysis class. There's a number of theorems, and you have to be careful with this, that you want pointwise convergence to imply LP convergence, or L1 convergence, or even just convergence of the Riemann integral. So when alpha is unbounded, you have to do some approximations, and it's not that tricky, but it's non-trivial, let me say. It's, well, tricky is a relative term, so I won't go there with that. All right, so the L2 ergodic theorem uses L2, and you remember one of the great advantages of L2 is the inner product. And then you can talk about orthogonality and other nice features that come out of the inner product. And the L2 ergodic theorem is functional analysis or infinite dimensional linear algebra. And it's the way I'm going to state it is a general version of it. Concerns operators, but if you just apply it to our Koopman operator, then you get the L2 version of the mean ergodic theorem, as it's sometimes called, the operator ergodic theorem, or von Neumann's ergodic theorem. And remember, our operator, the Koopman operator, has norm 1, L2 norm. And so it satisfies this contraction. Sometimes these are called contractions, or more properly, non-expansion. So the setting is to have a general Hilbert space with perhaps a complex valued inner product. And in our case, in L2, remember our inner product is the integral of alpha beta conjugate d mu. And we need one more definition, which hopefully you saw at least in finite dimensional linear algebra, that if you have a linear operator, it has an adjoint with respect when you have an inner product, or in other words, you're in a Hilbert space, that you, whoops, made a mistake here, that when you take the operator in the inner product on the right and bring it across, you get the adjoint. All right, that's like the definition of the adjoint. And in finite dimensions, at least in the real case, the adjoint is just a transpose. So you can just check with the usual inner product. When you bring the operator from here and then associate with here, you get a transpose. Okay, so that's the basics of Hilbert spaces that we're going to need. And here's the operator version of the theorem. And remember, if you want to think concretely, you should be thinking about the operator as the Koopman operator and the Hilbert space as the L2 space of some probability measure. All right, so let's say we have a linear operator, and as I said, it's non-expansive. And so we have a norm condition here. And we look at the stuff that's fixed by the operator. All right, so in our case, where we're thinking about the operator as the Koopman operator, the projections, the space M, are the things that are fixed by the Koopman operator, which is the same as saying that alpha star composed with f equals f. In other words, it's the invariant functions almost everywhere. So this space M is, well, it's the fixed points of the operator, but in terms of the usual ergodic theory applications, it's the space of almost everywhere, L2 now here, invariant functions. So we have an orthogonal projection. Another nice feature of having an inner product is you have a nice clean orthogonal projection. Then the theorem is that this Birkhoff averages for every alpha, this average of the iterates of the operators converges to the projection to the fixed point space of the linear operator. All right, so if we interpret that in terms of our usual case, it's saying that there's this L2 function, alpha star, for which this sum, the usual Birkhoff sum, converges to alpha star, but now in L2. All right, so these are, if you remember your analysis, L2 convergence and pointwise convergence in general are different things. So here's a couple simple examples. Here is a rigid rotation in 2 dimensions. This, you can check, this is rigid rotation. It preserves the unit circle, and so it has norm 1. This is all L2 norms here, or usual Euclidean norms. And the only fixed point is 0. All right, so that means if we iterate this guy, we end up getting 0. when we average. All right, now when we iterated, in fact, if we take an initial vector, when we iterate, we rotate around the unit circle. If we start with something on the unit circle, we rotate around the unit circle. But the way they add up and average, when you take this 1 over n, you get 0. So that's not hard to do, especially in complex coordinates. So we may see that in Homer. Now another example is the one we talked about before, but now it's in a different context. It in fact does have a fixed vector because it does have an eigenvalue of 1, and the fixed vectors are the span of 1, 1. You can just check that this times this equals 1, 1. And so you can also compute explicitly here, when you average these guys, you remember this is either this or the identity. You add them up, acting on this, you end up with a over 2 plus b over 2, a over 2 plus b over 2, and that's already in the span. All right, so the limit is actually in the span, which is where it should be. It's the projection of the initial thing here onto the span. All right, so notice this A could be different than B to start with. All right, so the initial vector is not in the span of fixed vectors, but when you average it out here, you do get something in the span, which tells you that this projection here. So that last bit was not quite right, so I censored it. All right, so let's start the proof. So one of the things, if you're not used to Hilbert space, is that, well, a linear subspace is closed under finite linear combinations. All right, but it's not necessarily a topologically closed subspace under the topology. All right, so it's closed under finite linear combinations, but it's not closed under limits. All right, so remember we're in infinite dimensions, so we don't have a finite basis. All right, so here's M. So this guy you can check is actually closed because this is a continuous operator, and if you take a limit of things in here, they still satisfy this. All right, so it's closed, and we let n be the closure of the linear subspace alpha minus u alpha. All right, and the first project is to show that these two subspaces give a nice decomposition of the Hilbert space. In other words, we can write the Hilbert space as the direct sum of the two as an orthogonal decomposition. All right, and so for that, what we have to show is that one of these is the perpendicular of the other. And so we're going to show that M, remember M is our fixed point space, is equal to the perp of this guy. All right, and so remember what the perpendicular is. It's all the vectors that are perpendicular to everything in here. All right, so actually this is an n here. I should be clearer. Okay. All right, so let's see. So remember what we're trying to prove here. We're trying to prove this equality. So we're going to do the usual thing and do one inside the other. So let's do something in n perp. So this means if alpha is in n perp, it's perpendicular to everything in n. In particular, it's perpendicular to all the terms that look like beta minus u beta, because those are the things that generate n. So let's just see what that buys us. So we just use the fact that the additive, the linearity of the inner product, we get this 0 equals this. We use the adjoint and we bring it across. First we distribute it and we get this. All right, so here we move from here to here by taking the adjoint. And so now we get, again, a usual trick in linear algebra, we get that whatever this is it's perpendicular to every vector beta. All right, so if you're perpendicular to every single vector beta, then in fact you have to be 0. So if this guy is 0, then that means, of course, that it's a fixed vector of the adjoint. All right, but we want it to be in script M, which means we want it to be a fixed point of U itself. All right, so once we have that it's a fixed point of U itself, we would get that alpha in here is also in M. All right, so we have to show it's a fixed point of U itself, and here's the argument for that. Again, this is all just kind of very simple inner product linear algebra, but we compute this norm squared. Norm squared is the inner product of a thing with itself. We multiply it out via linearity, and we use in these, we bring across the adjoint. All right, now we know, we're assuming here that the alpha is a fixed point of the adjoint, so we get alpha, 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 norm alpha squared, and the whole thing just works out to be 0. All right, so that means that the norm of this guy is 0, which means, in fact, the vector is fixed, and so that's what we need to get that the perp is contained in M. All right, now for the other way, all right, so let's say alpha is in M. Now, that implies immediately that U alpha equals alpha. That's the definition. Now, we use the argument we just did on U star, all right? And we want to get that U star star of U is equal to U. We know, we know this is true. And the argument we just gave, it gives U star alpha equals alpha. But we have to show that the norm of U alpha star is less than or equal to 1. All right, and so to prove that, that's pretty easy. We look at the norm of U star squared. We once again write it as the inner product with itself. We pull the adjoint over, and we use now here, we use the Cauchy-Schwarz inequality, that the magnitude of an inner product is less than or equal to the product of the two magnitudes here. So that's what I'm using here. And now we know that the norm of U is less than or equal to 1. And now we get U star of alpha. So we divide both sides by U star of alpha, and we get U star of alpha is less than or equal to alpha. All right, so what have we shown? We've shown that we can use this same argument here to get that U alpha equals alpha implies U star alpha equals alpha. And so we basically do the same trick, and now we compute alpha beta minus U beta. We use linearity, we bring the adjoint over, we bring it back in, but now alpha minus U star alpha equals 0, because that was the whole point of this rest of this page. And so we get 0. So this means that alpha is perpendicular to everything of the form beta minus U beta. And since these generate, that suffices to get that alpha is in N hat. And so we get that script M is in script N perpendicular, and therefore they're equal. All right, so summarizing where we're at, we've written H as a nice orthogonal decomposition. All right, and so let's see what that buys us and why we actually did this. So this means if we're in H, we can write any vector or function or element of H as a unique sum, as some element of N and some element of M, and that element of M, orthogonality, right, when you have an orthogonal decomposition and you have a point here, it's decomposed into a pair of vectors, which you get by taking the orthogonal projection onto the two subspaces. So that tells us that the second, if we choose alpha, then this, in fact, another mistake, that when we use this decomposition, if we choose alpha naught here, so just giving a name to that. Then the other element is P of alpha. All right, so we're projecting down onto M, and that's the projection where, remember, P is this orthogonal projection. All right, now we've taken alpha and we've written it in two pieces, one piece in N and the other piece in M. All right, so we're going to take the limits we care about separately. So we're going to show that if we compute this limit here of the averages of the operator, that if you hit this element, it converges to 0. It'll go away. And this element, in fact, is the identity when you pass it to the limit. All right, so if we put these pieces together, when we look at this averaging of alpha, then we write alpha as alpha naught plus P of F here. Sorry, that's P of alpha. I keep doing that. And that converges to P of alpha. All right, so this piece of it goes to 0, and this piece of it goes to itself, which is P alpha. All right, now one of these is very easy. So this guy, if you're in M, remember that U beta equals beta. So that means U to the I of beta equals beta also. So when we compute this sum, each one of these is just beta. So we get 1 over n times the sum of n betas. So we just get beta. All right, so this part B is easy. So we now have to prove part A. We have to show that if we're in script n, then we go to 0. All right, so one part of this is easy, but the tricky part is that we had to take the closure of n in order to get a proper decomposition of the Hilbert space. So let's say we look like gamma minus U alpha. So let's say we're a generator of script n. So we compute this guy, and now that we get a standard issue telescoping sum, that when we take 1 over n with this sum, we get 1 over n gamma minus U to the n of gamma. And now we take this guy, this sum, and bound it in norm, and we use the triangle inequality. We change the minus to the plus, and U to the n of gamma, the operator norm of U to the n, that's just a little argument here, is also 1. And so this is bounded above by gamma. So this is a fixed number, n goes to infinity, and that then yields the 0 we need. But this is only for the case when you're a generator. All right, so the thing that we have to take care of is when you're a limit of a generators. All right, so here we were a generator. Now we have to take the limit of such things. So now we look at J and let alpha J be generators, in other words, gamma J minus alpha J, and converge to alpha naught. All right, so we do kind of a standard inequality that one would do in such a case to do an approximation, is we add and subtract the term with alpha J in it, and then use the triangle inequality. So here we put an alpha J in a -1 and a +1, and then use the triangle inequality, so we get this term and this term. All right, and then we'll deal with those also in standard ways. We estimate each term. So first we use the convergence of the alpha J's to alpha naught. We can choose J, this is a J here. We pick J so that alpha naught minus alpha J is less than epsilon over 2. We know we can do that since these guys converge. All the norms are 2 norms. And then we estimate this term, and we first use triangle inequality, bring the norms inside, and then the fact that the norm is submultiplicative, and then use the fact that this has norm 1, and we end up with n copies of epsilon over 2. We get epsilon over 2. All right, so that tells us how to pick J. And now for this J, pick n so that this sum is less than alpha over 2. All right, so why is this possible? Well, because we know that alpha j is a generator, it's of this form, and we showed that this limit goes to 0, so we can pick n large enough that this is less than epsilon over 2. All right, so now we've bounded both terms in star here, and therefore we get that this is less than epsilon. All right, but epsilon was arbitrary, so this guy goes to 0, and that finishes the proof. So we've worked with two parts of the sum here, the one in m and the one in n, and computed the limits in both cases.